Okay, we're going to just finish up the last few slides we have to go, and that's about it, I think. All right. So we've been talking about obviously here our last chapter, which is nuclear chemistry. And last time we talked about a couple of things. We talked about first order kinetics, which is again how basically all radioactive decay follows. So all radioactive decay follows first order kinetics, which really, as we saw, is our same sort of kinetics equations that we did when we talked about kinetics at the beginning of the semester. The two main equations, obviously, is the natural log of A is equal to our natural log of A naught minus KT. And also our half-life equation for first order, which is the natural log of 2 divided by K. What we did see is, again, sometimes these sort of concentrations here that we did in kinetics are a little bit different in terms of nuclear chemistry, in terms of the units and stuff that we see. But this is still sort of your final sort of concentration. That's still your initial. And really, the K here is usually referred to as the decay constant instead of the rate constant, as it's a measure of obviously radioactive decay. And our time here is our T. And again, sometimes they will use some different symbols. Again, sometimes you will see something like the natural log of n is equal to natural log of n naught minus KT. Or you may even see natural log of n is equal to natural log of n naught minus lambda t. Lambda is also used as another symbol for the decay constant, depending on sort of your book. N means nuclide, sort of our guys going through radioactive decay, or nucleus, our isotope that's going under. Our normal sort of things that we do want to think about as we use these equations, again, is the idea that you want to make sure the unit of time here is the same in both of those. And especially in these type of problems, a lot of times they are in different sort of units. Some may be hours, days, years, weeks, so we've got to make sure those guys are always in the same unit of time. The other thing that's very common as well in these sort of radioactive decay sort of problems is using both of these equations together is oftentimes what you have to do. Because it is radioactive decay, they oftentimes will give you maybe the half-life, or you could look up the half-life of whatever you may be looking at. And the half-life obviously is the time it takes for half of whatever we started with to basically disappear. So super common, like a number of the examples that we did, you kind of use the half-life equation to get the decay constant. Once you have the decay constant, then you can solve for whatever you may be looking for, which may be maybe the final concentration, maybe time. In addition, as I mentioned earlier, in terms of the units, for A, it doesn't have to be concentration. A lot of times, again, like we saw, milligrams maybe for each of those, or grams. We could also do some type of radioactive decay, or rate of radioactive decay, like counts per minute per gram of carbon that we saw. So those are, again, some common sort of units. As long as those initial and sort of final concentrations are the same units, you're good. Again, could be a rate, could be grams on both sides, could be milligrams. It could really even be percentages on both sides. It doesn't really matter as long as they are really the same units, so everything cancels out correctly. The other thing that we talked about last time as well was the idea of binding energy. And binding energy is really sort of the energy that's released sort of in the process of fission. There we go. In the process of fission, there's sort of a difference in the mass of sort of the nucleons, which is our protons and neutrons, stuff that make up the nucleus, and the mass of the isotope that we end up with. And that is what's sometimes referred to as the mass defect. And the mass defect is that difference in mass of really the components of the nucleus and the mass of the isotope itself. And that's sort of going to get converted into energy through this fission process. And you could calculate the binding energy in a couple of ways. I could use kind of like equals mc squared, which is our sort of Einstein equation. And the way that we do this here is the mass here would actually be the mass defect. And that basically is found by taking the number of protons times the AMU of protons, or atomic mass of protons, plus the number of neutrons you have times its atomic mass of a neutron. And you subtract it really from the atomic mass of that isotope. And that will give you your mass defect, which is really what the M in sort of this Einstein's equation represents. C is our speed of light, which is a constant, 3 times 10 to the 8 meters per second. Now, as we talked about, when you do this calculation, if you choose to use Einstein's equation and you put all those numbers in, you will end up with units of AMU times meters squared divided by second squared. And what your goal would be to end up with is kilograms times meters squared over second squares, because that equals basically a joule. So that is where, if you did use sort of the Einstein equation here, this is where we would divide by Avogadro's number to the 26th, which, because we're taking to the 26th and not 23rd, that takes us to kilograms basically, and that would get you kilograms meters squared second squared, which equals a joule. And there's really kind of 2 common units of binding energy that's sometimes calculated, and that is joules per nucleon. And again, a nucleon is basically your protons and your neutrons, the particles that make up the nucleus. And the other sort of conversion, or common units, is mega electron volts per nucleon. And you could also get that by taking Einstein's equation through this process, and you could use a conversion that there's 1.602 times 10 to the minus 13 joules in a mega electron volt. Or you can just straight up take the mass defect in AMU, and you can use that other conversion that we saw, which was an AMU is 931.5 mega electron volts. And that would get you there as well. So you can take that mass defect and just go straight into that. And you could also divide it by the number of nucleons to get to the mega electron volts per nucleon. A reminder that binding energy per nucleon is another measure of stability. So the higher the binding energy per nucleon is, the more stable that particular isotope is. So I think we did 3 of them last time, and what we saw was very similar to what we saw in that graph, which was the iron there was the most stable, as it had the highest binding energy per nucleon versus the other 2 that we did in that particular case. Any questions on any of that stuff we talked about? Yeah.
But this particular, like, is it only subject units?
Say it one more time. Does it always? Uh-huh. No, these are, the final answer is basically one of these 2 is usually the common unit. So it can be joules per nucleon, or mega electron volts per nucleon is also a very common one. So it kind of depends sometimes on the textbook as to which one they kind of go with. So we've had textbooks in the past that, you know, kind of do the mega electron volts, and we have some that do joules and some that do both. So I think yours kind of does both, I think, if I remember correctly. But those are really the 2 common sort of units that you see. Other questions? Okay, so then let us finish up talking about some of this stuff here. So nuclear transmutation is a way in which we can really sort of, I'll say, upset maybe some nucleuses, and it will end up becoming perhaps another element along the way. So fission, for example, can occur spontaneously, so you can have sort of an unstable nucleus. And remember that really a fission is where we have this nucleus that kind of separates out into 2 new nucleuses. Usually will give off some neutrons and some energy along the way. One way that you could sort of promote somebody kind of changing into something else is basically shoot a particle at it, and you can use a particle accelerator, right? Accelerator here, like that, where we have a magnetic field and electrical field, where basically it just kind of then shoots the particle at it. And that's how a lot of these sort of, for example, man-made elements are also discovered. But in these cases here, shooting these alpha particles, say at nitrogen, gets us these oxygen, and then aluminum will get us some phosphorus here in this process. So this is what is sometimes referred to as the transuranium elements, and a lot of those, again, which are those man-made ones, the ones with the good names like californium, einsteinium, berkelium, and all those kind of guys. That's basically how they're sort of made. As you can see, they pretty much all start with some type of particle or something like that, really being sort of shot at another element. The result of that is going to become unstable and form some new elements along the way. And again, that's where a lot of those guys on the bottom of the periodic table basically do come from. And that is one way, as I mentioned a second ago, that you really can sort of kick off a fission reaction. So for example, here, if we had uranium 235, I think this is what it is. And if you shoot a neutron at it here, it's going to become uranium 296 and become a bowling pin and become unstable here. And what's going to happen is this guy is going to then split off into these two new nucleuses, giving off a lot of neutrons and also a lot of energy in this process as well. As we talked a little bit about earlier on in the chapter, this sort of fission reaction does generate a lot of energy. So you get something like times 10 to the 13 joules of energy per every mole of uranium that you use. And in comparison, if you took coal, for example, and you did a combustion of coal, it's like a 10 to the 7th. So a lot more energy is given off in these sort of fission reactions than in a traditional chemical reaction. And again, a lot of that has to do with, again, chemical reactions is all about electrons and breaking and making bonds. Here we're getting into the nucleus, which is a lot of change that has to occur, a lot of energy that changes in that particular process. They also compare these two things because that is the two traditional ways for a long time that we get power, right? So we get power by burning coal, and we also have like nuclear fission sort of power plants that we use to get power. So you can see you get a lot more energy out of the fission sort of reaction. Now, when it does break apart into sort of those two new nucleuses, for example, when it does go through a fission reaction, you don't always get, for example, the exact same two guys always forms as a result of it. But there are some with common mass numbers here as to what usually will form, but it's not always going to be exactly the same two guys every single time that this sort of fission reaction occurs. So in a fission reaction, it's important that certain factors maybe don't occur, or if certain factors do occur, it may not be such a great thing. And that's because we can have what is sometimes referred to as a nuclear chain reaction. And in a nuclear chain reaction, it's basically a self-sustaining reaction that occurs when fission basically begins. So if you have the right amount of some type of fissionable sort of product there to start with, basically what happens is this reaction will basically continue to grow. So if you think about what we saw a second ago, basically one way you could start this reaction is basically shoot a neutron at uranium, and then that gets you your new nucleuses and some neutrons and some energy. The problem of this reaction is what you make on the product side is actually kind of what you use to start the reaction. So it can kind of go back around, if you will, and start the whole reaction again. And if it does that, obviously every time it sort of does that, your reaction starts to grow exponentially. Now, as a result of these sort of fission reactions, it's obviously given off a lot of energy every time that sort of reaction occurs, not to mention a lot of radioactive waste products every time that sort of process occurs as well. So it gives off a lot of energy, and obviously that could not be a good thing in certain cases. The one way that you could kind of maybe keep it under control is to use basically what's sometimes referred to as less than the critical mass needed. Critical mass is basically the amount of fissionable material like uranium, for example, that you need to keep this reaction just going and keep building. So if you keep it less than that, a little non-critical, you could kind of keep the reaction a little bit under control. This is sort of like a nuclear bomb type of situation here. They have a subcritical mass of uranium separated from each other, but obviously when the bomb hits, along with some explosion there, your kind of wedge goes in there and completes it. And now you have a critical mass of that, which will obviously kick off, obviously, that fission reaction, giving off a tremendous amount of energy. And the other really bad part of that, obviously, is all that sort of radioactive waste products, right, that are sort of made as a result of it, which stay around for a very, very long time. Now, when we were talking about earlier, the idea of power plants, basically all power plants, for the most part, kind of work the same. Most of them does traditionally. You basically have a source of water, and you heat up that water. When you heat up that water, you create steam. Steam goes out to the turbines, to the generators, and you get light. Yes, when it turns on. They also then can kind of cool down that water, right? We'll take it back, that steam back to liquid water and kind of the process. So in a traditional power plant versus, say, a nuclear power plant, really the difference is the heat source there for how you heat the water. In a traditional power plant, coal was burned, like we talked about there a second ago, that combustion of coal. And the energy from basically burning coal is used to heat the water and so forth. In a nuclear power plant, they use a fission reaction to basically generate enough heat to heat up that water. And because it's obviously radioactive, they usually need to keep that sort of shielded from the rest of the sort of the process here. So, and this, which is sort of a split diagram of a nuclear power plant, we have basically where the fission reaction occurs in here. And we have what are referred to as fuel rods. And fuel rods are basically, in the case of this, little pellets, if you will, kind of like erasers of uranium stacked in there, and that's going to allow the fission reaction to occur. As the fission reaction occurs, obviously it generates a lot of heat, and they have a water sort of reservoir in here. All that water in there gets super, super hot, right? And obviously that heats this other sort of reservoir of water, which is a little further away from the nuclear fission reaction that's occurring. That obviously creates our steam and out to our generators. Again, cooling that back down brings the water back in. That is why nuclear power plants are usually found a lot of times near a very large body of water, right? And ours is over there in San Onofre, those two big concrete domes that you see off the 5 freeway. I don't think they're working anymore, but that's where they were, obviously right by the ocean. Usually if it's not near a big body of water, they will have very big, what they used to call cooling towers, big things of water basically to use to do that in that process. So why this is reaction on a nuclear power plant not go crazy or dangerously like that is they keep a couple of things to keep it sort of under control. They use less than the critical mass of uranium. So obviously by keeping less than a critical mass, it hopefully will prevent the sort of chain reaction from occurring, and obviously not a good situation if that should occur. They also have these things here, which are also control rods. And control rods are things that are kind of soaked in things like cadmium and such. And cadmium, things like that, are really good neutron absorbers. So why would being able to absorb neutrons be good in this type of reaction? It is because this reaction starts with a neutron, right, to your uranium, and it also makes neutrons, right? So if you have these things, they sort of take out some of the neutrons from the reaction. It's able to keep it under control and stuff like that. And so that's how it sort of keeps itself running in a relatively safe-ish manner. Now, there is obviously some downsides to both sort of ways that power is traditionally sort of made. Obviously, in a coal powered plant, there's a lot of pollutants that is given out into the environment. Same thing, actually, in a sense, with the nuclear power plant. It generates a lot of new elements that are formed as a result of these fission reactions, where frankly, they have half-lives of thousands and thousands and thousands of years, which means they are very, very active for a very long period of time. And what do you do with all that? People never wanted it to go anywhere. So for a lot of years, most nuclear power plants would kind of store all this stuff on their sites because nobody wanted it traveling through anybody's town or going anywhere. In Nevada, they dug a big hole for a lot of that, and I think they've started using it in the last 5-10 years, maybe, I think. But before that, a lot of them would keep all this stuff sort of on site. So obviously, it creates a lot of radioactive waste that hangs around for a very long period of time. And as you can see here, what is sometimes occurs in terms of that when we have a fission reaction is sometimes referred to as spent fuel. And spent fuel is sort of the byproducts of the fission reaction, basically those guys that are being formed as a result of it. And just in general, you can see in terms of storage time, that's a lot of years to store that stuff, why they're still pretty radioactive. So that does bring up a lot of, issues in terms of, who stores it, who keeps track of it. Some of this stuff obviously can be used for not so good things if it sort of falls into maybe not so good hands and stuff like that. So for a lot of years, that was really a very big issue. Like I said, I think they've now started using the place in Nevada, which is how they keep all the neon lights on in Nevada, right? Is from all that waste that they have going on in there. Thank you for not laughing. All right, so the other thing as well, a lot of our nuclear power plants, for the most part, aren't really working anymore because there's a lot of costs to try to bring them up to, say, code, if you will, and stuff like that. So a lot of them are sort of powered down in a sense and not really used all that much anymore. I think the last one in San Onofre, if I'm not mistaken, shut down not too long ago in terms of full sort of use. Now let's talk a little bit about fusion, which is a little bit different than fission. Fusion is sort of a little bit opposite. It's when we take basically two smaller nuclei and kind of put them together to make a larger one. Right? So a couple of hydrogens making some larger guys here. So smaller guys making bigger guys. This usually occurs at really, really high temperatures, like you took a vacation there on the sun type temperatures, the super large temperatures along the way. So fusion, two smaller guys coming together in really, really high temperatures. Again, fission, really, you could start it off with a neutron, unstable nucleus separates out into two new nucleuses. So sort of the opposite sort of process that occurs. To finish up on this chapter here, we do use obviously radioisotopes in medicine. And as we might have talked about earlier, obviously you would be looking for something that has a much slower, smaller half-life, right? You wouldn't want something with a really long half-life. Otherwise, your follow-up exam would be a really long time. So you want something probably hours, maybe minutes, days at the most. So here are some things that are used. Sodium-24 is a blood tracer. Iodine is used for the thyroid gland. Technetium 99 there is used for imaging. One nice thing about isotopes, even radioactive isotopes, is that they basically will do the same chemistry as the non-radioactive isotopes, say in the body. So you can put it in there and basically follow what's going on by really following the radioactivity. And obviously you can do some imaging as well to follow where everything is ending up. In addition, and I think they still do it, and it was very common years ago as well, that they would implant some radioactive sort of things in tumors and stuff like that to try to shrink them. So you can be used for a lot of things. Here's a bone scan. As you can see, all the sort of radioactivity sort of highlights the different areas along the way. And again, those things will kind of behave the same way as sort of non-radioactive guys will in your body. When you do use something that's radioactive, this is a very common tool that's used a lot while you're using it, while you're cleaning up. And this is a Geiger counter, and a Geiger counter has a cathode and an anode, and basically it will kind of beep when it gets near radioactive sort of material. And it will beep a lot louder as you get closer to really radioactive sort of material. So oftentimes if you're using it, you will be running around the room with a Geiger counter to make sure, you didn't contaminate, hopefully, the entire laboratory. We used to do that when I worked in school. We had to go around and everybody was in charge of making sure, the place is not glowing. Other sort of things that you sometimes would also use when you're using maybe radioactive in a lab is they usually make you wear like a little ring and like a little badge. And they used to have film in them years ago. And again, every so often they would develop them and see how much exposure you obviously got from your experiments and stuff like that. So there's a lot of safety things. And as we talked about earlier as well, it's really important if you ever find yourself working with anything that's radioactive, that you do some research yourself and make sure you understand what type of emitter it is and, what safety precautions that you need. Again, depending on the type of emitter. And as we saw earlier, alpha particles don't go as far as say as gamma rays. So if you're using something that's a gamma emitter, you want to make sure that you have the proper sort of protection for yourself. And usually exposure time is also really important. Keeping that at a minimum is usually a good thing to do. Speaking of that, sometimes it's referred to as a RAD, which is a radiation absorbed dose. And there's sort of an equivalent for man, which is a REM. And it's basically a RAD times a quality factor. And as you can see here, if you're doing something with gamma or beta, it's 1 versus an alpha particle, which is 20. That doesn't go as far. So, you can expose yourself a little bit more to those than the other guys. But we do get, by the way, if you had a Geiger counter, if you just held it up in a sort of a non-radioactive-ish area, it will go off. Yeah. So it will, hopefully not loudly, but it will go off. It will beep a little bit. And that's sometimes referred to as background radiation. And there's a lot of sort of background radiation that we're exposed to through cosmic rays, medical and dental, X-rays, air travel. If you happen to be living next to a nuclear waste place as well, I suppose, gives us some exposure. So we are sort of exposed to some of this, obviously, depending on what we're doing and where we're at. And there's sort of a background level that, there is. But definitely, if you are using anything, you should always make sure that you understand what you're using. Again, sometimes people aren't always, I don't want to say upfront, but remember to tell you important things like, hey, you shouldn't be standing over that all day with nothing on, right? You should have some protection and stuff like that. Any questions on any of that there? That is strawberries. Good talk. All right. All right. Congratulations. That wraps up Chem 15.